MERKLE trees are an essential concept in blockchain and cryptography. However, even though they might sound complex, they are based on a simple idea: hash functions. A function is just a rule that takes an input and produces an output. For example, given a food name, the function returns whether it is hot, cold, or could be both. A hash function, in particular, is any function that takes an input of any length and produces an output of fixed length. For instance, a function accepts the name of your favorite food and returns 1 if it is hot, 2 if it is cold, and 3 if it can be both. As a result, by converting the output to numbers, we have turned our function into a hash function. As we allow the function to return a wider range of results, we need to increase the number of digits in the output. For example, a function might take the name of a city and returns a number corresponding to the country it is in. However, this is not a hash function because the output is not always the same length. In order to accommodate all countries, the function output must be a larger number. As a result, we need to pad the output with zeros to ensure it is always the same length. And now we have a hash function again. An important property of a hash function is that it is deterministic. This means that for the same input, the function will always produce the same output. No matter how many times we ask the function what the country of Paris is, it will always return the same result. Mathematicians have studied different hash functions and have found that some are better than others. And they can be used for any type of data, from text to images, and not just for food or country names. For instance, the one used in Ethereum takes an input of any length and produces a deterministic output of 256 bits. Most programming languages already have built-in functions that can hash data using these hash functions. And this is very powerful because it allows us to come up with a unique fingerprint for any piece of data. This unique fingerprint is called its signature, or simply its hash. Now imagine you have a transaction object like this one. Remember, a transaction looks just like a JavaScript object with a sender, a receiver, and an amount. You need to convert it into a single string so that we can hash it. For example, you use this function to convert a JavaScript object into a string. When you call the hash function, it takes the string and produces a unique fingerprint of 256 bits. Remember, no matter how many times you hash the same string, you will always get the same fingerprint. Now take another transaction and do the same thing. Convert it into a string of bits and hash it. You end up with another unique fingerprint of 256 bits. As you can image, you can combine these two fingerprints and hash them together, and you get a new fingerprint of 256 bits. You start with two fingerprints of 256 bits, and you end up with a single fingerprint of 256 bits. Next, you take another pair of transactions and hash them together, and you get another fingerprint of 256 bits. And this process continues until you end up with a single hash. Eventually, you will get a single hash per block, and each block in the blockchain follows the same pattern. With the hashes of a set of transactions in a block, you get a single hash of 256 bits. Next, we combine it with the hash of the previous block to get a new hash of 256 bits. Remember that the blockchain is public, so anyone can add a new block to the chain. However, the blockchain is secure because hashes are very sensitive to changes in the input. If you wanted to alter an existing transaction, you would break the chain of hashes. Then everybody else would instantly know and discard your changes. On top of that, adding a new block to the chain requires respecting this chain of hashes. In addition, miners must also gain the approval of the other miners, following a consensus mechanism which I will explain in another video. This guarantees that new transactions are valid and that the blockchain is secure.